Hi everyone, welcome back. So this time we're going to be going into what is weight. Let's make sure I don't block out part of this. I'll move myself over here. There we go. So what is weight? Well, weight is a gravitational force your body feels due to a planet's mass. Now there's a big fancy equation for gravitational force. We simplify it. Actually, that equation is vastly simplified using this right here. This gravitational constant is the acceleration due to gravity. It's how fast you accelerate when you're falling towards the ground, roughly, because that's in a vacuum. And that's actually taken by taking the mass of the Earth, this fancy constant, and your average distance from the center of the Earth. So there's a lot that goes into that, but on Earth, it's going to be equal to 9.81 meters per second squared or 32.2 feet per second squared. Now, as a note, that's actually not 100% accurate. Depending on where you are on the Earth, either way up high or down low in a trench, that will be different. There are actually some good fluctuations. Like there's a place in Nepal which has, I think, like 9.77. Doesn't seem like much, but it is. Like it's a little bit of a boost. Actually, if you look, and this is kind of a little fun thing, if you look at like where the world records and the high jump have been, and where and pole vault, all those kind of things, some of that is probably due to differences in gravity. Mind blown, I know. Because think about it, on the moon, I can jump super high because there's very little gravity. Okay, it's not that big on the Earth, but you know, there's a small change. Okay, now the great thing about this equation is that you know the acceleration. You always know what it is as long as you're on Earth. It's either 32.2 feet per second squared or 9.81 meters per second squared. And so from that, you can calculate your weight. It is your mass times that acceleration. Now here's the very, very important thing. Pound mass doesn't work in this equation. Don't use it, ever. Pound mass is a bad unit. Don't use it. The unit to use, if you're trying to use the English system of units or the American Engineering Standard, it's going to be slug. Slug is the correct unit of mass in the American Engineering Standard system, and kilogram in the metric system. So if you use those, then everything will work out fine. If you use slugs and this acceleration, it'll pop out pound force. If you use kilograms and this acceleration, it will pop out newtons. Newtons and pound forces are the units of force. Okay? So remember, slugs work for the American Engineering Standard System. Pound mass does not. Okay, now what about pound mass? How is it going to help me at all? It's only actually good for weight. Pound mass only has one use, and that's for weight. You're like, but you just said not to use that equation. You're right, I did, because pound mass kind of builds it in. I say kind of, because on Earth, I want to say this a billion times, on Earth, and only on Earth, and only with regards to weight, 1 pound mass has a weight of 1 pound force. The number is the same. Never use pound mass otherwise. Don't use it for mass otherwise in any other equation. Don't use it in an equation at all. Only use it for this one helpful conversion. If you need to use some sort of mass unit and you can't use kilograms, use slugs. That will work out nicely. But do not use pound mass. It'll mess everything up. Okay. So if we're looking at this, weight equals mass times gravity. We have 10 times 9.81 gives us 98.1 newtons. And 32.2 times 10 is 322. If you wonder why the difference in these boxes is so extreme, 10 slugs is way more than 10 kilograms. I actually should have emphasized that more. This box right here should be much smaller in comparison to the 10 slugs. If we're just going by size of box, it'd be size of mass. So just because they have the same number does not mean they're the same amount. Be very careful with that. Someone says they're going to give you 10 slugs of, gold. Take that over 10 kilograms. You'll be much richer. Okay, let's keep on moving on. The last thing we're going to talk about is how things connect and your common units. So for these equations so far, they connect through mass. You have your weight equation, which has mass in it. You have your force equation, which has mass in it. So if you solve for mass, then you can plug that into your force equation. This is what's typically asked to do. It will give you somebody's weight in mass, or a car's weight in pounds or newtons. And it'll say, okay, you apply a certain force, what's the acceleration? If you have a certain acceleration, what's the required force? And so it's expecting you to calculate your mass using that weight. Don't plug in the weight, that's going to mess you up. But you're going to calculate your mass using that weight. And so it looks something like this. You'll have the force equation at the end that looks like that. Another thing it might ask you to do is to say, okay, given maybe you're falling or you're trying to lift into the air, what's your acceleration? And what you have to think about is that weight is one of the forces that's going to be resisting you rising into the air or helping you fall. That's what you're trying to do. And so that would have to be added in with the other forces. That's the two ways they usually connect. Okay, as for units, it's actually super easy because there's only newtons and pound force. There's something called a dyne. If you're wondering what that is, it's not important for this class. But to convert newtons to pound force, there's one conversion for it. It's simply that 1 newton is 0.225 pound force, so 10 newtons is 2¼ pounds. You probably thought it was going to be harder. It's not. The only thing to remember, though, is that a kilogram times meter per second squared is a newton. And a slug times a feet per second squared is a pound force. Don't forget that because you will have to simplify things. You might get confused, like, I've got kilogram meter per second squared, but I needed newtons. You have newtons. You just have to realize that it's a named unit. And so it's made up of these other little base units. When you have them all together, it's just newtons. And that is in your conversion sheet at the front of your book. So use that to your advantage. Well, that's it for force and weight. I hope this helps you, and I will see all of you next time. Bye-bye.